And what you see is that every time you have a jump in the charge sensor, it means a charge is being added to that particular chain. And everything that happens here in between is because of the long-range Coulomb interaction. So in order to set up our simulation and to get these Coulomb drag and the excitons going, we need to first of all go into this regime where we have a chain or two chains that are tunnel coupled along the chain, but no hopping in between the chains. And the way we measure this tunnel coupling is by simply taking a line scan along a diagonal, along an interdot line, and then you see that the charge is being recorded, like the signal is being recorded by the charge sensor, and depending on how big your tunnel coupling is, you will have a more broad or a more narrow line here. And from there you can directly read out the tunnel coupling if you fit it with the right formula. And here, just as an example, I'm plotting two variegate voltages, and you can see that within just 100 or few tens of millivolts, we can turn the hopping completely on or completely off. At the same time, however, we want to also maintain Coulomb interaction. And measuring the Coulomb interaction is also pretty straightforward. We simply take, again, these gate versus gate maps, and the size of this interdot will tell you how much your Coulomb interaction is, because it's simply, that distance here. So we see that in the whole area, we still have a sizable Coulomb interaction, while we have turned off the hopping in between the two chains. And now we are ready to set up the simulation for these excitons, and I will guide you through these plots. They're a little bit convoluted, but we start in this configuration where we have one charge on each side in the upper chain, and no charge on any of the sides in the bottom chain. And then we look at the charge sensor response while we pulse on each gate individually in the top channel. And we start with this configuration, and then we simply pulse on this level. What happens is a hole will go out of the system, which is equivalent to, say, loading an electron. This will actually push a level in the bottom channel a little bit down, but not as far as to go below the Fermi level, and therefore nothing happens in the bottom channel. And you can see that the bottom left sensor picks up a negative signal, and the bottom right channel also, the bottom right sensor also picks up a small signal, and then when you start to shuttle the electron to the other side, you see that the signal goes up because the charge is going away from the left side and is going towards the right side. What you can do now is to change the energy of the bottom channel, push it a little bit down, and once you're close to the Fermi energy, what happens is that when you now load an electron in the top channel, you're actually loading a hole also in the bottom channel, so you're forming an exciton. And because the bottom left sensor is closer to the bottom channel, it will be more sensitive to what happens in the bottom channel, and you see that here now the signal is reversed. And now if you transfer this exciton to the other side, you see that, again, the positive signal that we had here is now decreasing because the exciton is going away, and here it's going towards the right sensor. So we have successfully shown that we can statically, slowly transfer the exciton from one side to the other. The next thing that we want to show is that we can actually also measure it in current. And for this, we need to speed up the process quite a bit. And what we did here is we shuttled a little bit faster. So here you see the shuttling time to shuttle from one side to the other. Here we're actually going from this side to this one, and we're looking at we're measuring the current at here, and what you see is that there is a positive current, so a current coming out of this ohmic, and a negative current coming into this ohmic. So a net charge transfer from right to left. At the same time, we have a negative current measured here, and a positive current measured here, which means a net charge transfer from left to right in the bottom channel. And you see that more or less the magnitudes of the currents, they match, which means that despite the fact that we have a net charge transfer in both channels, overall the system is an insulator. So this is equivalent to having an exciton insulator. All right, so let me conclude. I have shown you that we can use these systems as a nice Fermi-Hubbard simulator. So again, I have this table showing you the magnitudes that we can achieve. And especially, we're able to nicely control the tunnel couplings, and also we have some control over the Coulomb interaction. And we have observed the exciton formation and transfer through the structure. I also want to briefly advertise the work from Shin and Lisa. They're also working in our group. They have the same kind of device in a different fridge, and they have managed to tune up the whole device and have exchange tuned up among all the pairs in the channel. And this is now an interesting platform to study some phase transitions or other things that are dominated by exchange interaction. Yeah, and with this I would like to conclude, and thank you for your attention.
Questions? So can you extract something like an exciton binding energy?
Yeah, that's something that indeed we want to understand a little bit further. In, let's say, in the static way, when we're just transferring a single charge every time, it's pretty hard. Maybe from the current measurements we could. Unfortunately, they're pretty preliminary, especially the fact that we are measuring the current through the charge sensors is quite limiting us. So we have now made new devices where we have contacted directly the channels. There it might be easier to actually extract something like a binding energy. Yeah, what we can definitely say is that the appearance of the excitons happens at a value of this energy of the bottom channel that is like not the smallest Coulomb interaction term that we have in the area, but more or less the average Coulomb interaction that we have between the areas. So that could be more or less binding energy equivalent.
But do you have any estimate? Is it consistent with what you might expect from just having two adjacent quantum dots?
It is consistent with what you would expect. Yes, it is proportional. It is actually equal to the Coulomb interaction. So.
Any other questions?
Thank you. You had very lovely results. I guess I have a question of, do you have a comment on, say, the lifetime of your excitons, and is there any plans to do anything else with the excitons other than transporting them from one end to the other?
Yeah. So the lifetime of the excitons, I think we first need to look into the coherent evolution of the excitons. In this particular system, I think it's too small yet so far to really see some coherent evolution. So what we are envisioning to do is to make the device a little bit bigger. In principle, this kind of design that we are chosen is scalable to some extent. It's going to be harder to control, but in principle it's scalable. And once you have enough sites and enough space, you can look into things like quasi-exciton condensation and project times and stuff like that.
Gosh.
I have a quick question. So, do you think this material could have any topological alternatives?
Maybe. On top of my head, I wouldn't say yes or no, but could be that in the right architecture, in the right geometry, you can find some stuff. There is work where they are trying to couple the semiconductor to superconductors and then look into my random kind of physics. Yes, but I don't know if that's the kind of topology that you were looking for. Maybe something more like.
Just because you have like currents propagating in common.
Yeah. Okay. No, I haven't thought about that yet.
All right, well, let's thank Daniel again.